In our previous lecture, we discussed how the set of systems can be divided into two classes, linear systems and nonlinear systems. And we stated that linear systems obey superposition, while nonlinear systems do not. In this lecture, we'll review some characteristic behaviors that occur only in nonlinear systems. We'll review 5 phenomena that occur only in nonlinear systems. And I should say at the beginning that any particular nonlinear system may show one or more of these phenomena or may not show any of them. The first phenomena we'll discuss is finite escape time. Finite escape time means that the output of the system can go to infinity in finite time. So it can start from some initial condition, and even with no input, the output can go off to infinity in a time less than infinity. A linear system will never display this behavior. The output of a linear system can go to infinity, but it can only do this in infinite time. For example, like a ramp signal, the output goes to infinity, but does not go to infinity until the time reaches infinity. From a real-world viewpoint, no signal ever goes to infinity in finite time. But what this means, in terms of real-world systems, as opposed to their mathematical models, is that the output becomes large in a manner that is not exponential. It becomes large faster than any exponential function. The second phenomenon, which occurs only in nonlinear systems, is multiple isolated equilibria. For you to understand this, let me first define what an equilibrium is. An equilibrium is a constant output of the system when the input x is equal to 0. So the system starts from some initial conditions. If it has an equilibria, then the output is constant from these initial conditions. So for example, consider the linear system y dot plus y equals x. If we set x equal to 0, there's only one equilibrium solution. That would be y equals 0. No other constant value of y will satisfy the equation y dot plus y equals 0. But if we have a nonlinear system, there can be more than one constant output of the system. For example, y dot plus y times quantity y minus 1 equals x. That is a nonlinear system. If we set the input x equal to 0, there are two possible solutions to that equation. One is y of t equals 0, and the other is y of t equals 1. So there's two equilibriums that the system can have when the input is 0. This only occurs with nonlinear systems. Linear systems can only have one equilibrium or an infinite number of them all connected together. For example, the linear system y dot equals x. If we set x equal to 0, there are an infinite number of solutions to y dot equals 0. If we set y equal to any constant, it will satisfy y dot equals 0. Let's now look at a system with multiple isolated equilibria. This system is the banana, and it is a nonlinear dynamic system. Its motion is governed by nonlinear differential equations. Now we know this is nonlinear since it has multiple isolated equilibria. Now I don't want you to attempt this at home. These nonlinear systems can be unpredictable, and you never know when they're going to go to infinity. The output of this system is the orientation of the banana, and an equilibrium is a position where the orientation does not change. This system has two isolated stable equilibria. Here is equilibrium number 1, and here is equilibrium number 2. This is a rather silly example, but I'm not joking. These are actually the equilibria. If we put the banana in other positions, it will return to one of these two stable equilibria, and we can't put it in any position in between. So these equilibria are isolated. Let's look at solutions as a function of time for the two equations that we just discussed. The linear equation, y dot plus y equals 0, and the nonlinear equation, y dot plus y times y minus 1 equals 0. For the linear equation, we mentioned there was only one equilibrium, and this equilibrium turns out to be stable, so nearby solutions, in fact all solutions, will end up converging to this equilibrium, as we've shown in the graph above. For the nonlinear equation, y dot plus y times y minus 1 equals 0, there are two equilibria. There is the equilibrium y equals 0, and then there's the equilibrium y equals 1. As it turns out, the y equals 1 equilibrium is stable, and the y equals 0 is unstable for this system. So you can see solutions starting with other initial conditions will tend to converge to the y equals 1 solution. The important thing for you to remember at this point is that only nonlinear systems will have multiple isolated equilibria. And so if you notice this behavior in a physical system, you know nonlinearity must be present. The third phenomenon that we only see in nonlinear systems is limit cycles. Limit cycles are persistent oscillations of the output that can occur when the input is 0. And these oscillations are consistent even when initial conditions are varied. That is, we'll get the same cycling oscillation in spite of the variation in initial condition. So for example, a system with a limit cycle might display a graph of oscillation in the output as shown in this figure. You notice we start with various initial conditions, but after some time, all the oscillations converge to the same oscillation. The oscillation is periodic, but not necessarily sinusoidal. If the system shows limit cycle behavior, you know the system must be nonlinear. The fourth phenomenon that we only see in nonlinear systems is subharmonic or harmonic oscillation. In response to a periodic input, the output of a nonlinear system may have a larger or smaller period. For a linear system, if we put in a periodic input, the output must have the same period. It's very easy to show this behavior with a simple example. So we'll look at the system y is equal to x squared, and we'll use an input x of t, which is a sine wave with period t1. When we square the sine wave, the negative parts become positive, and we'll get a signal which is always positive and has a period that is 1/2 that of the input. So here you see this nonlinear system has an output with a different period than the input. That can't happen with a linear system. If we put a sinusoidal input into a linear system, the output will have the same period as the input. What's this? We have a visitor from the world of linear systems. And it's saying that actually I'm wrong. Linear time varying systems can display subharmonic and harmonic behavior. Huh. Well, please tell me more. Oh, I see. It's that these systems are time varying. This example that you give, y of t equals x of 2t, well, that does a time dilation. It's basically taking the original signal and it's, of course, squeezing it. Huh. Well, that is a linear system, and it does change the period. So I guess you're right. But the students haven't discussed time-varying system. That's coming up in a later lecture. So I need to give them some sort of rule that will help them understand when subharmonic or harmonic behavior will occur. That's a very good point. That's very helpful. A linear time invariant system will never have subharmonic or harmonic response. If the input is at a particular frequency, the output will come out at exactly the same frequency. Since linear time invariant systems are the main topic of this course, we'll see that for the vast majority of systems that we'll discuss in this class, that they'll have this property. And so if we see a system out in the real world which is not time varying and it displays subharmonic or harmonic response, then we know that that system has to be nonlinear. The last phenomenon of nonlinear systems that we'll discuss today is chaos. Now you've heard of chaos, I'm sure. It's a very popular topic in the media. What is chaos? Chaos is a bounded aperiodic output that is highly sensitive to initial conditions. The three important terms in this definition are bounded, aperiodic, and highly sensitive. It's those aspects which make chaos chaos. So what does chaos look in terms of an output? If we start with several different initial conditions, perhaps very close to each other, we'll get a response y of t for each initial condition. And these responses will stay bounded, that is, they won't go off to infinity. They'll be aperiodic in the sense that they'll never repeat. And because they're highly sensitive to initial conditions, they'll diverge one from another. They won't stay close to each other. For a linear system, if the trajectories stay bounded, they must stay close to each other. So they cannot be highly sensitive to initial conditions. From an engineering viewpoint, chaos is something one really doesn't want in one system. Engineers like things that are predictable and repeatable, and chaos is not. Many nonlinear systems do not show chaotic behavior, but chaotic behavior only occurs among nonlinear systems.